Hi everybody. In this video I'm going to do an example problem involving one-dimensional motion in which an object has been thrown straight up either from the edge of a tall cliff or from the top of a tall building or from a tall tower, etc., so that after the object has reached its maximum height it can fall past the point from which it was launched and keep going down. In this problem we're going to have some approximations. The first approximation is we're going to ignore air resistance. Now it turns out at the speeds involved in this problem, air resistance actually starts to matter. We're going to ignore that, so this will be an approximation. Once we've ignored air resistance, then all we have to worry about is gravity. So we'll have a problem involving constant acceleration with the acceleration due to gravity. The acceleration due to gravity at the surface of the Earth is 9.80 or 9.81 meters per second downward. So that brings us to our second approximation. We're going to approximate the magnitude of the acceleration due to gravity to be 10 meters per second instead of 9.80 or 9.81. G, remember, is the magnitude of the acceleration due to gravity. So G is a positive number, but the acceleration could be positive or negative depending on how we choose our directions. I'm going to work using my y-axis to be vertical, so we'll have motion along the y direction or negative y direction. So I'm going to use y as my position coordinate, v sub y as my velocity component, a sub y as my acceleration component. So I've written my equations for constant acceleration in terms of those y-related variables. And just for reference, I've got the definition of the instantaneous velocity and average velocity in one dimension for the y component. Final note before we get started, just a couple notation things. V sub 0 y and v sub y 0 are interchangeable. V sub 0 y means the velocity at time 0 y component, and v sub y 0 means y component of the velocity at time 0. Means the same thing. I may flip the subscripts as I work the problem. Don't worry about it. Last thing, delta just means change in. So delta y would be y minus y sub 0, for example. All right, let's get started. The first thing I want us to do is to check our signs, and more generally to check the self-consistency of our setup. So right here, this indicates that I'm choosing my positive y direction to be upward. I could have chosen down as the positive y direction. I'm choosing up as the positive y direction. Here I'm indicating that the position at time 0, the y coordinate at time 0, I'm setting that equal to 0. So I'm measuring everything from the launch point of the ball. So locations above the ball will be positive locations. Locations below the ball will have negative y coordinates, negative locations. All right. This arrow is indicating the initial velocity of the ball, the initial y component of the velocity. I've said that the initial velocity in the y direction is positive 20 meters per second. Now, if up is the positive y direction, then a positive number here should represent an upward direction. So that's all self-consistent. So everything looks good. All right, the next step is to determine our acceleration. Now we know we have a condition of free fall and we're ignoring air resistance, so the only acceleration is due to gravity. The magnitude of the acceleration due to gravity in our approximation is 10 meters per second. The direction is downward. All right, so if up is the positive y direction, but our acceleration has this magnitude and is downward, then the acceleration itself should be minus 10 meters per second. And meters per second squared means meters per second. All right, so the next thing I'd like us to do is fill out this table. So what we're doing this for is we're going to use our y position as a function of time and y component of the velocity as a function of time, and just fill that out. We're just going to use these equations to fill out this data table for times 0, 1, 2, 3, 4, 5 seconds. All right, so to do that, we need to plug in for the information that we know. So first, for the y component of the velocity, v sub y, that's the velocity in the y direction at time t. V sub y 0, that's the velocity in the y direction at time 0. That's this, positive 20 meters per second. So we can plug that in. And then our acceleration in the y direction, that's this negative 10 meters per second, so we can plug that in. So I'm going to take this and put it up here with those numbers plugged in. So all I've done is flip the sides of the equation. My v sub y is here, and then this side of the equation is right over here. So here's my v sub y 0, and this is the acceleration, and there's the time. Great. So while we're at it, let's just fill in this table. So at time 0 seconds, I can plug that in for t. 0 times this gives me 0, and I'm left with 20 meters per second for the y component of the velocity at time 0, which is just what this means. So that's a good check. All right, at time equals 1 second, I could plug that in for t. I'd have negative 10 meters per second times 1 second. That will give me negative 10 meters per second. Add that to 20 meters per second, and I'll be left with 10 meters per second. At time 2 seconds, 2 seconds times negative 10 meters per second is minus 20 meters per second. Add that to 20 meters per second, and I'll have a velocity of 0 meters per second. So I'll just leave as 0. At time 3 seconds, plug that in for this time here. 3 seconds times negative 10 meters per second. So I'd be adding a negative 30 meters per second to 20 meters per second. I'll have minus 10 meters per second. At time 4 seconds, negative 10 meters per second times 4 seconds gives me negative 40 meters per second. Add that to 20 meters per second. I'll have negative 20 meters per second. And finally, at 5 seconds, doing the same thing. 5 times 10 is 50. I've got a minus sign, so I've got negative 50 meters per second plus 20 meters per second gives me negative 30 meters per second. All right, before moving on to the next row, let's just look at this pattern. Each second, the velocity changes, the velocity in the y direction changes by negative 10 meters per second. I go from 20 meters per second to 10 meters per second to 0 meters per second to minus 10 to minus 20, minus 30 meters per second. All right, that's what this acceleration right here means. The velocity changes by 10 meters per second per second. Acceleration is the rate that the velocity is changing. All right, let's look at the second row in our table. Now we're going to look at the position as a function of time. We'll do the same thing. This is the position at time t. Y sub 0 is 0. This is the 20 meters per second, the velocity in the y direction at time 0. Then I have 1/2 the acceleration. The acceleration, again, is negative 10 meters per second, times time squared. So I'm going to take this and put it over here. So I've had to kind of crowd that in there. I flip the sides. Here's my y sub 0, my v sub y 0t, plus 1/2 acceleration, negative 10 meters per second, t squared. All right, let's do the same thing. We're going to plug all these times in and see what we get. So when we plug in times 0, I'll have 0 here, 0 there, and I'm just left with 0, which shouldn't surprise us. Our initial position was 0, and that's what we're left with. All right, at 1 second, plugging in 1 second for the time, 20 meters per second times 1 second gives us 20 meters. Hold that thought, 20 meters. I'll have 1/2 times negative 10. That's negative 5 meters per second. So negative 5 meters per second times 1 squared gives us negative 5. And the second squared cancels these seconds squared, so I'll be left with negative 5 meters for all of this. So 20 meters plus a negative 5 meters gives us 15 meters. We'll do one more. At time t equals 2 seconds, I'll have 20 meters per second times 2 seconds. That gives me 40 meters. Hold that thought, 40 meters. 1/2 of 10, that's 5, and I've got a negative, so negative 5 meters per second squared, but 2 seconds squared, so that'll be 4 times second squared. The second squareds cancel, so I'll Negative 5 times 4 gives me negative 20. So 40 plus a negative 20 gives me 20 meters. And you can do the same thing for t equals 3 seconds, t equals 4 seconds, and t equals 5 seconds. I'm going to pause the video, or actually I ask you to pause the video, fill those out yourself, and then we'll restart and you can check your answers against what I put in. So pausing the video in 3, 2, 1. All right, we're back. Hopefully you paused the video and fill this in. I will fill it in myself right now. Boom. And this is what you should get if you filled in the table. All right, let's take a look at this. Putting all this together, at t equals 2 seconds, the y component of the velocity went to 0. That means it's in between going upward and going downward. That means at time t equals 2 seconds, the object has reached its maximum height. So its maximum height turns out to be 20 meters above the point of launch, because we've taken our y equals 0 value to be at the point of launch. So all our y values correspond to values measured from this launch point. So the object reaches a maximum height of 20 meters above the point of launch. All right, so either side of the time for maximum height, there's an interesting symmetry that happens. So at time t equals 2 seconds, the object is at its maximum height, and its y component of the velocity is 0. Let's go 1 second to either side of that. At t equals 1 second, the velocity was 10 meters per second upward. And at t equals 3 seconds, the velocity was 10 meters per second downward. Same speed, but different velocity directions. One is upward, one is downward. Let's go over 1 more second. At t equals 0 seconds, the velocity was 20 meters per second upward. At t equals 4 seconds, the velocity was 20 meters per second downward. Same speed, but different directions for the velocities. Let's look at the heights themselves. Go over 1 second from the time for maximum height, and we have 15 meters for the height at time 1 second, and 15 meters for the height at time 3 seconds. And those heights are measured from the initial launch point. Let's go over 1 more second. At t equals 0 seconds and t equals 4 seconds, both 2 seconds removed from the time for maximum height, the height is 0 meters. That means, basically, looking at this, it takes 2 seconds for the object to reach maximum height, and then 2 seconds for it to come back down to where it started from. Pretty cool. All right, so the point of all of this is actually that we don't need to stop here. We could plug in any time, and given this information, we could have found the position and the y component of the velocity at any time, as long as this object is in free fall. At 6 seconds, 12 seconds, 1.3 seconds, 3.7 seconds. Plug in the time in this expression, you get the y component of the velocity. Plug in the time in this expression, you get the y coordinate. All right, so this is a very important point. If we know the initial position and the initial y component of the velocity, and if we know the acceleration component, then plugging in any time, we can get the position and the y component of the velocity at any later time. And this is true for any one-dimensional motion with constant acceleration. It doesn't have to be y direction. This could be in the x direction or the z direction, whatever coordinate you've set up. All right, very cool. All right, so let's now move to the next question. Let's imagine that we didn't do any of this. We'll leave it here for reference. But let's imagine we didn't do any of this yet. And let's imagine that the very first question that I asked you was number 4 here. Find the time for the object to reach maximum height, and then find that maximum height. And by finding maximum height, I mean how high does it go above the launch point? All right, so we could cheat and look here. We say, well, I already know at 2 seconds it's reach its maximum height, because that's where the y component of the velocity is 0, and I know it reaches 20 meters above its launch point. So the maximum height is 20 meters, and the time that it reaches the maximum height is 2 seconds. We're going to pretend we didn't do any of this. We want to do it from scratch. All right, so we could go to these 2 equations, and you could just guess. Say, let me try this one. So you try plugging in here. You'd plug in your y sub 0. You'd plug in your v sub y sub 0. We have that information. But you don't know how high the object goes, so that's one unknown. and you don't know how long it takes to get to maximum height. So that's two unknowns in one equation. So you could just start with this, and you'd get stuck, and you realize you have too many unknowns. So you've got to go to something else. All right, so let's go to this. Let's rewrite this right here, and then let's plug in our known information. So I'm going to hold on to v sub y for just a moment. But v sub y0 is 20 meters per second. That's the initial velocity. That's the velocity at time 0, y component. The a sub y, that's minus 10 meters per second per second. The time, that's our unknown if we're trying to find the time to maximum height. And then we have v sub y. You might think, oh, maybe we have another unknown. But this isn't actually an unknown. We're looking for the time for the object to reach its maximum height. We know something about the y component of the velocity at the maximum height. At the maximum height, it's in between going upward and going downward. So the y component, the up and down component of the velocity will be 0. All right, so we can solve for the time. I'll do that in a couple steps. I'm going to subtract 20 meters per second from both sides. All right, I've got a minus and a minus. That's good, because if I divide both sides by negative 10 meters per second, I'll get a time of positive 2 seconds, and I want a positive time. All right, and that does in fact correspond to the answer we already knew to be true, because we'd already done this second by second. But if the second by second calculation hadn't matched up, this would be the way that you would go about finding the time to get to maximum height. All right, a couple of important possible pitfalls I want to point out. Sometimes people, they see this and they're really cavalier and they're just doing examples and they flop these. Well, that would be wrong, right? If you flop these, you would be saying that the object at maximum height had a velocity of 20 meters per second and that it started out with an initial velocity of 0. But if it started out with an initial velocity of 0, it would just fall, all right? So that'd be non-physical. Furthermore, if you flip them and had positive 20 over here, then when you divide by the negative 10 meters per second, you'd get a negative time. All right, so I see often on exams, people do that, and then they just drop the minus sign and think it's all going to be good. And at most, I'll lose a couple points. Well, no. You've completely fundamentally misidentified two important things in the problem. So even though this is a simple equation, that's actually really important. Making it worse, you can actually make two mistakes and get exactly the right number. For example, if you put the 20 meters per second here, that would be wrong, and the 0 here, again, wrong. But then instead of having negative 10 meters per second corresponding to your coordinate system and the acceleration, you instead had positive 10 meters per second, you would have gotten positive 2 seconds. You'd have the right answer, but had two mistakes instead of one. All right, so this is not to just bust on everybody, but to point out that it's actually really important to understand what you're doing. Okay, now that we know that it takes 2 seconds for the object to get from launch to maximum height, we could plug that 2 seconds into here to find the location corresponding to t equals 2 seconds. The location corresponding to t equals 2 seconds will give us the maximum height. So let's take this and write it here. This gives us our y component as a function of time. Now everything in here is known. Y sub 0 is 0, v sub y0 is positive 20 meters per second, a sub y is negative 10 meters per second, and the time, we're going to plug in time equals 2 seconds because we want the time corresponding to the maximum height. So if we plug in t equals 2 seconds for the time, this y will give us the y corresponding to maximum height. So let's rewrite this with all those things in there. That gives us this. And if we grind through this calculation, we get y equals 20 meters, just like we had before. But this is how you do this, finding the time to maximum height and finding the maximum height from scratch. All right, I'm going to put this information right here so we don't forget it. So there's the summary of our result. The object reaches a maximum height, y max equals 20 meters. So that's both the maximum value of the y coordinate, and it also corresponds to 20 meters above the point of launch. And this happens 2 seconds after launch. OK, there's actually another way to find the maximum height without finding the time to reach maximum height. And I'll show you that now as soon as I clean the board. All right. In order to find the maximum height without finding the time to get to maximum height, we can use this third expression I've written here. This says the square of the y component of the velocity at the endpoint in time is equal to the square of the initial y component of the velocity plus 2 times the y acceleration plus the change in y, which could be y corresponding to this v sub y minus y sub 0, which corresponds to this v sub y 0. All right, so let's rewrite this right here. And what we want to find is the change in y. We want to find the change in y from the initial instant until the thing reaches maximum height. Now, delta y is just equal to y because our y sub 0 happens to be 0, but we wouldn't have had to set our y 0 equal to 0. So I'll just leave this as delta y for now. So let's plug things into this expression. V sub y 0 is 20 meters per second, so we have to square that. I have 2 a sub y. A sub y is negative 10 meters per second per second. I have my delta y, that's my unknown. And then my v sub y, what's that? Well, v sub y 0 is the velocity at time 0. V sub y is the velocity at time t corresponding to maximum height. Now we're not looking for the time. Instead of having a time interval, we've got a space interval. This is the velocity at the beginning of the interval. This is the velocity at the end of the interval. At the end of the interval, the thing is at maximum height. So this v sub y is the y component of the velocity at maximum height, which is 0. All right, I can solve all this for delta y. I'll do that in 2 steps. First, I've got to subtract this 20 meters per second squared from both sides. And then I've got to divide both sides by this. This gives us minus 400 meters squared per second squared. This gives us minus 20 meters per second squared. The result will be 20 meters. Which indeed was our maximum height. All right, so that's a way you could get the maximum height without finding the time to maximum height first. Finally, in the last part of this problem, we're asked when the ball is 25 meters below launch. That is, how long does it take the ball to go from launch all the way up to maximum height and then back down to some location here 25 meters below the point from which it was launched? So first, we should identify where that is. 25 meters below launch corresponds to y equals minus 25 meters. We want the time at which this happens. All right, probably the simplest way to attack this is to use our position as a function of time expression right here, because we have all the ingredients we need. We know the location, negative 25 meters, at the time of interest. We know the initial location. We know the initial velocity in the y direction. We know the acceleration. All we're looking for is the time at which this position y equals negative 25 meters happens. All right, so let's write this right here. Here we go. And then let's plug in all our information. So we have y equals negative 25 meters. Y sub 0 is 0 meters. V sub y 0 is 20 meters per second times time plus 1/2 negative 10 meters per second times time squared. And then I'm going to rearrange this. All right, so this is nominally how we would align this with our position as a function of time expression. But what we have is a quadratic expression. Right? We have a t and we have a t squared. So we need to whip out the quadratic formula. So to do that, I need to get that in terms of 0 equals a constant plus something times a variable plus something times a variable squared. So I'm going to do that. I'll add 25 meters to both sides. So then I'll have 0 equals 25 meters plus 20 meters per second times time. Plus, I'm going to combine these things, so I have minus 5 meters per second t squared. All right, so in our quadratic formula expression, which nominally has this form, we need to identify the coefficients of our squared term, our first power term, and then our 0th power term. So this is the way you usually see the quadratic formula expression set up. Usually it's written in terms of lowercase a, b, and c. I've used uppercase a, b, and c to avoid some confusion. My acceleration is negative 10 meters per second, but I have a half in front of this, so that makes my so-called a term, if I want to identify the t squared term with this x squared term, my a term to be this, but this isn't the acceleration. So I want to use a capital A instead of a lowercase a, just to avoid that confusion. You might also be confused. You might be saying, well, this is in terms of x's and this is in terms of t's. Well, right, but x is just whatever variable we happen to be working with. I could change the x's to t's without a problem. In fact, why don't I do that right now? There, all better. The x's are now t's, and it corresponds to this. So with that mapping, this is a, capital A, not to be confused with the acceleration, which is negative 10 meters per second. This coefficient here is capital B. This coefficient here is capital C. So all we need to do is plug those into here, or equivalently, if you have a nice handy-dandy graphing calculator with a quadratic formula function on it, just probably type in your A, B, and C. There's probably a routine to do this and spit this out. What I'm going to do, in case you don't have that, is just rewrite all this with this information in it. Here we go. That gives us this. If we plug and chug those numbers, we get t equals positive 5 seconds and also negative 1 second. Now, the negative 1 second was before this stuff started even happening, right? Our clock started at t equals 0. So t equals negative 1 second is before our problem, and we can eliminate that, although I'm going to return to that in just a moment. So this happens at t equals 5 seconds. And look at that. We still have this information left over. When we are calculating this out second by second, at t equals 5 seconds, the position did turn out to be y equals negative 25 meters. But this is how you could have found that information from scratch. OK, I want to talk briefly about the minus 1 second. This isn't part of our problem. But if we imagine instead this equation right here or right here extending for all time, what would negative 1 second mean? Well, here's what it would mean. So first imagine our actual problem. I've thrown the ball upward. At time 0, it's at y equals 0. And then after 2 seconds, it's gone to its maximum height. And then it comes back down. But imagine someone from really, really, really far below has thrown up another ball. And that other ball passes the ball that I throw, and it passes my hand just as I'm throwing this ball up. And imagine that just as I throw this ball up with an upward velocity of 20 meters per second, that this other ball is coming in parallel with it, and at the instant it passes my hand when I throw the other ball up, also has a velocity of 20 meters per second. And that these balls then travel together. So the question I could ask is, when was that other ball 25 meters below my launch point? The answer is that would have happened 1 second before I threw the ball. That's what this negative 1 second corresponds to. So sometimes, even when you have an answer that's outside the range of your problem, there's an interesting story that goes with it. So this is a relatively straightforward way to go. Just take your position as a function of time formula, plug your stuff in, and then solve for the time. If you don't have a nice way to handle the quadratic formula, it becomes a bit tedious because then you've got to do that by hand. But on the other hand, if your graphing calculator can take care of the quadratic formula stuff for you, then this is not only conceptually simple, but also procedurally simple and very reliable. However, if you don't want to deal with the quadratic formula, there's another way to go. And back in the old days, when we didn't have graphing calculators that could do this stuff out for us, and we had to do it all by hand, we were always looking for other clever ways to do these types of problems. So here's one other such way. I'll leave the result here. All right, here's the other method. So we know we launched the ball at time t equals 0. And the ball goes up to its maximum height, and then it comes back down. So instead of trying to do it from the beginning, let's reset the clock at the top. All right, so let's imagine if I was given this problem to do from scratch. Maybe I hadn't done problem 4, or maybe I had. Either way, I'm given this problem, and I want to find the time it takes to get to a point 25 meters below launch. I could split this up. I could find the time to max height and find max height, which I did in part 4, and then find the time from max height down to here. Starting from maximum height simplifies things, because if you restart your clock there, if you take a new time, so instead of calling it time little t, maybe call time capital T, and I'll use that, set time capital T equal to 0 when the ball is at its maximum height. You'll have a new initial velocity. At maximum height, the initial velocity would be 0. That wipes out this linear term in t, making the equation simpler to solve. All right, so if we imagine doing this from scratch, maybe we've done nothing, and we want to find the time from launch until it's 25 meters below the launch point. We'd break it in steps. We'd find the time to maximum height. That's 2 seconds after launch. We'd have to find the maximum height as well. That's 20 meters. Then we'd want to find the time from maximum height down to here. So that's what I'm going to set up. All right, so I'm going to take this equation, and I'm going to use it in a slightly different form. I'm going to subtract y sub 0 from both sides. So subtract y sub 0 from this side, it's gone, and then y minus y sub 0 will be delta y. So I'll have delta y equals v sub y 0 t plus 1/2 a sub y t squared. And now what I'm going to do is I'm going to set a new time. And I could still use this little time t and just keep track in my head that I'm restarting my clock. Or what I'm going to do is I'm going to use a new time t. So I'm going to use delta y equals v sub y 0 capital T plus 1/2 a sub y capital T squared. And I'm going to let capital T equals 0 at maximum height. All right. If capital T is 0 at maximum height, v sub y sub 0, now I probably should create a new symbol for that, but that's just too much for me to keep track of. This will be, starting now, this 0 is going to correspond to capital T equals 0. All right, so this new v sub y 0, maybe I should use a different symbol for v, but I won't, is now 0. So I've got 0 times my time, that'll kill that term, plus 1/2. My acceleration is still 10 meters per second downwards, so still negative t squared. Now I've got to do my delta y. That's my delta y from where I'm starting my clock at maximum height down to here. This is 20 meters. This is 25 meters. So to go from here to here, I'm dropping 20 meters, then dropping another 25 meters. So the delta y is minus 45 meters. All right, I can divide both sides by this. I should have just multiplied by 2 rather than dividing by 1/2, but it's the same thing. If I do that, 2 times 45 is 90. I got a minus sign. Minus 90 divided by minus 10 is positive 9. The units are going to be seconds squared. So I've got 9 seconds squared. I've got to take the square root of both sides, and I'm going to get capital T equals 3 seconds or minus 3 seconds. All right, we started our clock at capital T equals 0 at maximum height. So what that means is 3 seconds after that, the object is 25 meters below our original y sub 0, or 45 meters below maximum height. All right, now t equals 3 seconds. That's the time from maximum height to this location we are interested in. We had another 2 seconds to get to maximum height. So the total time would be this 3 seconds plus the 2 seconds it took to get to maximum height, and that gives us 5 seconds, which agrees with the answer we calculated earlier. The answer before we actually started our clock also has some interest. We have a ball here at capital T equals 0, whose velocity is 0, and it takes 3 seconds to fall down to here. But if we imagine throwing another ball upward that just reached this point with 0 velocity at our capital T equals 0, that ball would have had to have been thrown at capital T equals minus 3 seconds. All right, that's all for now. I hope this example was helpful in understanding how to use these 3 important equations for motion with constant acceleration in 1 dimension. I also hope this example helped illustrate how these equations fit together. And finally, I hope this example helped illustrate that there's often more than one way to attack a problem. All right, thanks for watching and see you next time.